Mr. Bainey, and we're going to take a look at, hey, what's up, Math 1? We're going to take, hello, this is Mr. Bainey. Here we have lesson 21.2, Aas Triangle Congruence, and we're in a new module here, but in the previous module, module 20, we saw 3 theorems for triangle congruence, in addition to the use of CP/CTC. So just to kind of recap, we did in lesson 20.2 was ASA, the next lesson was SAS, and then in 20.4 we did SSS. So we have those 3 theorems, and here is the 4th one, AAS, which stands for, you've probably guessed it, angle, angle, side. And this one is sometimes confused with the first theorem that we came across, which is, this is not the same as ASA, but very, very similar in that they both have 2 A's and they have 1 S. What's important here is where the S is located in both of those, right? In our first theorem, we had S kind of in the middle, in between the 2 angles. And then here we have the S, or the side, is not between the 2 angles. So that's going to be applied to our triangles where the side is not included. Here in the book, it's going to mention it as non-included side. So we still need 3 pairs of parts to be congruent between triangles to know that the triangles are all congruent. And those 3 parts happen to be 2 pairs of angles, right, just like our first one, but the non-included side this time. And just to show as an example, if we're looking at angle A and angle B in this first triangle that you see at the bottom, then the included side is AB in between those 2 angles that we're focusing on. Now these other 2 sides, AC and BC, those both are the non-included sides. So what's nice about AAS is that we actually have 2 sides we can choose from that are non-included, that we could apply this AAS theorem. Here on the next page, you'll see the statement of AAS triangle congruence. And I'm just going to point out here that we still have the same conclusion as the last 3 theorems, and that is the triangles are going to end up being congruent. Remember that triangles being congruent, that means that we now know all 6 parts, corresponding parts will be congruent, right? But before that, we don't know all 6 are congruent. That's why we want to get to this conclusion. But we at least need to get 3 pairs of parts, and that happens to be the 2 angles and the non-included side. On page 1056 is a proof. Let's go ahead and work on this one. So we're going to use the AAS theorem to prove that these triangles are congruent. We are given, I'm not actually going to write this down in the proof, but we're given all of this information. So when I start my proof here, my 2 columns, I'm not going to write down the whole given statement because you see it there at the top. Okay, but do get in the habit of doing that. Don't do what I'm doing. Now, statement number 2, before we actually write down and figure out what that statement is, let's mark our picture. Angle ABC is congruent to angle DEF. And that's this angle here in the picture and this other angle. So those 2 are both congruent. The next part of our given is BC is parallel to EF. And if you recall, the way that we notate parallel lines, the way we mark it on a picture, is with these arrows. And those arrows do not mean the sides are congruent. Okay, so don't get that confused. We don't know that BC is congruent to EF. We have no clue. We just know that they're parallel, which means they're going to have the same slope. And then AC is congruent to DF, those 2 segments. So far we have 2 pairs of parts. We have a pair of angles. That's this one up here and this one. And we have a pair of sides, AC and DF. So we have 2 pairs of parts. Now we need a 3rd pair. And of course, we're going to be using the AAS. That's what it tells us in directions. So in order to do that, we just need to figure out what other pair of sides are congruent. And it's going to have to do with the parallel lines, because, parallel does not mean they're congruent. But if you have parallel lines, I'm going to trace this in purple here so you can try to see this a little bit easier. If I extend those two lines out, those are my two parallel lines. And then I'm going to draw this horizontal, or trace this horizontal line so that it intersects them both. It's going to look kind of like this. So there's my horizontal line. There's the side BC goes like that, and the side EF kind of goes like that. I didn't slant it as much, but sort of looks like that. It's having that effect. Now, if those two lines are parallel, these two, I'm going to mark them here in my kind of scratch work on the side. Then we want to figure out, well, what is congruent? What can we say is congruent because we have these parallel lines? And this goes back to, I want to say it's 19.2, which has to do with the angle relationships. And so I'm not going to write down what they are here, but I urge you to review those if you need to. And anytime you have parallel lines, you want to think back to those relationships. The relationships are corresponding angles, alternate interior angles, alternate exterior angles. If you find a pair of those, they're congruent all the time. We also have same side interior, but those add to 180 degrees. Again, that was just a quick little recap, so go back to 19.2 to review that. But we do have this angle right here is angle ACB and angle DFE. If on my scratch work, picture work out here on the side, it's these two. Okay, those two are related and they have to be congruent if we have these parallel lines. So first, let me write down the statement. Angle ACB and angle DFE. Those are congruent because, take a look at the picture on the right. This is one of four angles, right? It's the top left. This other one is also one of four angles here, and it's the top left. They're both in the top left, the same position or the same corner, so we call that corresponding. And when we have a pair of parallel lines and it's intersected by that transversal, right, that horizontal line, corresponding angles are always congruent. So the complete reason should be the corresponding angles theorem. But I'm okay if you just identify, if you know their corresponding angles, that's plenty. And statement number 3, we're done because we have our 3 parts. We have the angle here is angle B, the angle here at point C, and then we have this side AC. Now, keep in mind, AC is not included in between this angle and this angle. It's non-included, and that's what allows us to use AAS. Same thing on the right triangle. We have these two angles. This side DF is not included here. So that means our reason is AAS to state that the two triangles ABC and DEF are congruent. Okay, and that's it. Just 3 statements that we had to make there to do this proof. Here on page 1058, let's work with some triangles here on the coordinate plane, and I am just going to do one of these. I may not even do the whole thing, but we are given that angle A is congruent to angle D. So I'm going to mark that here on the picture, those two angles. Angle B is congruent to angle E. So I'm going to use 2 marks there. And we want to eventually show these 2 triangles are congruent. And if we're going to use AAS, AAS means that we are going to use 2 pairs of angles, which we already have. We don't need to prove that anymore. It's given to us. But we need our pair of sides. Now, the pair of sides to use AAS, remember, needs to be the non-included side. The included side is AB between these 2 angles and DE. And that means we want to show that BC is congruent to EF. Those are non-included sides. Or that, let me do a different color here, or that AC is congruent to DF, right? Those are also non-included sides. So if we did either the blue ones, showing those were congruent, or the purple lines, if those are congruent, then we know the triangles are congruent by AAS. In number 7 here, it actually tells us to show that the two triangles are congruent using AAS, which I just kind of walked you through. And we're going to use the distance formula. Since we're on a coordinate plane and these points, they have x and y coordinates, we can use distance formula to compare BC and EF. Those are the blue lines that I traced. So you'll just find BC. I'm going to do a shortcut here of the distance formula. If you try it out for yourself, you can see if you get the same thing. But I'll get 3 squared plus 4 squared. And that's 9 plus 16, which ends up being 25, which is 5. So the distance from B to C is 5. If you can show that EF is also 5, that means they're congruent, and therefore the two triangles are congruent by AAS. And in number 8, it's going to tell you to look at the lines that I traced in purple. That's AC and DF. I'm not going to do that for you, but just confirm that they are the same. And that's another method or another approach you could take, is doing AC and DF instead of BC and EF. That's going to do it for this lesson. As you're doing the practice problems, make sure that you're aware of the other theorems we've already done. This is the 4th one. We have one more to go. So any of the problems that you see from now on, right, you could be using ASA or SAS or SSS, or even the one that you learned here in this lesson. Okay, thanks so much for watching. I hope it helped. Have a great day.